Hello and welcome back to, I guess this will be the very last section of geometry from our Moise book. So, wow, it's been definitely a very long trip, just some of it was very tedious, but a lot of it, was hopefully somewhat educational. So anyhow, let's go ahead and conclude. Today we will be looking at the volume and surface area of a sphere. Okay, so basically a three-dimensional, I guess, circle in this case. So now the first thing I'm going to do is I'm going to go ahead and derive where the volume of a sphere actually looks like. But in order to do that, let's go ahead and draw one out first. So we'll go ahead and draw it on the side so you can see how that works out. So here is going to be our great circle for the sphere. And then we have the upper portion, and then there's also going to be the lower portion. Now for a sphere, there's not that much to work with because the only thing that we have is the radius of it. So we'll just go ahead and denote that as r over there. So r is going to be our radius. Okay. Now, in order to find out what the volume is according to the radius, we're going to have to kind of use a very non-conventional way of doing it, or very non-traditional way of approaching it. Okay, so here is what I'm going to do then. I am going to take a cross section of the circle. Okay, so I'm going to go ahead and take a cross section of the circle. So somewhere maybe like say over here and create a circle. And remember the cross section, they all should be actually the same thing. So if I slice horizontally elsewhere, you're just going to get another circle where it's going to be, I guess, just proportional to the great circle then. Okay, and then if I want to, I can go ahead and create another cross section somewhere else. But for right now, let's just go ahead and focus on that cross section. So for this cross section that I just created, which is blue over here, what I want to do is I want to go ahead and find out what is the area of that circle then. So from here to here, there is going to be a radius. And let's go ahead and say that that radius is going to be, well, let's just say A for right now. Okay, so the radius of that cross section is going to be equal to A. So let's see, where can I kind of put it so then that way we can see that. So that's going to be equal to A. Now, I feel like there are some other factors that we might want to consider, which will be the height or the distance from that circle to the center of the circle. So let's go ahead and say that that is going to be h then. So from there, hopefully you guys can kind of see it. The result is that I've created a right triangle where the radius of the sphere is going to be involved also as well, because if I draw that diagonal, you can see that the radius is equal to r. So right there, the relationship is that we have h squared plus a squared is equal to r squared, where h once again is the distance from the great circle to that cross section, and a is going to be the radius of that circle. Now, going back to what I was saying, I want to find out what is the area of that cross section over there. So let me go ahead and write that out. So the area of the cross section is supposedly equal to pi a squared. Now, what I want to do is I'm going to go ahead and do like a substitution because instead of a, I want it to be in terms of the other variables. So that's where this Pythagorean theorem comes in. So if I do a replacement, that is going to be equal to pi r squared minus h squared, and then that's going to be all multiplied by pi. If I multiply that out, that is going to be equal to pi r squared minus pi h squared, which doesn't look like it's too much because, that's pretty much as far as we can go in terms of cleaning it. But this right here, I hope you can kind of recognize that this is representing something else geometrically. This is representing something else geometrically. Now, look at the form of what we have right here, like how to find the area of this cross section. According to this formula that we just came up with, the area of a cross section is actually going to be the area that is between two circles, because you have right here one circle, which we have is pi r squared, and then minus another circle, which is going to be pi h squared. So if I were to draw that out, here's what it looks like then. Here, if we just have like kind of a generic circle if that's happening, r is going to be the radius of the outer circle, whereas h is going to be the radius of the inner circle. So here is going to be h, and then that is going to be this. So when I say pi r squared minus pi h squared, then what I'm finding is actually the area of what they call the annulus. Okay, annulus is another fancy word for saying the donut, because you have an outer circle and then you have the inner circle, and I want to find the region, the area of the region that is in between them. So that right there is going to be this. So that is going to be the annulus. I think that's how you spell it. Okay. Now, drawing that out as a cross section also, then that means that the picture of that annulus looks like the following. Let me go ahead and kind of move some of the stuff on the side if it's okay. Actually, I'm going to go ahead and erase this over here. The area of that annulus looks like the following then. So here is going to be the outer circle, okay? And then you're going to have the smaller inner circle. So these two shapes right here, right? The area of this annulus and the area of that cross section that I just drew right next to it, they have the same area then, because they have the same geometrical representation. Now, r, again, is going to be the radius of the sphere, and h is going to be the height of the circle. So that means that r is actually fixed. It never actually changes. The height, on the other hand, is going to be a variable because it changes depending on where you go. Now, let's go to another piece of the cross section so you can see how that works out then. So let's say we go a little bit higher to over here, where you can see that we have another cross section, and the result is probably going to be the same thing then. If I try to find the area of that cross section, we're still going to come up with the same area, but remember what I said. Pi r squared, that first part, that is going to be fixed. So that means that that cross section, that section is going to look like the following. You're going to have the outer circle, which is going to be pi r squared, minus pi h squared, which is going to be the area of the inside circle. Now, h in this case is going to be a lot bigger because the distance from the center to that higher cross section, well, that's a little bit higher then. So what that means is for this part right here, yes, you will have an annulus, but the radius of it is going to be, the area is going to be smaller because the hole inside the middle is going to be bigger then. So that is what it's going to look like then. And let me go ahead and take maybe one more cross section, so then that way we can have something to kind of play with a little bit. If I have, like, say, a lower cross section, then maybe like somewhere over here, and I don't want to, like, draw too many of these because that's going to be a little bit hard to look at. That one, your annulus is going to be the case where your outer radius is still going to be the same because it's r, which is fixed, but the inner radius, the h value, is going to be smaller because the height, the distance from the center to that circle, is going to be smaller then. So basically, you have a whole bunch of these cross sections that are stacked up on top of each other, which can be, I guess, morphed into these annulus, which have the same area then. If you put them all together, the question is, well, what does that actually look like? Well, here, let's look at a few more just in case then. At the very top, if we were to create this annulus thing, there's actually going to be no annulus. It's just going to be, well, actually, there's h is going to be equal to r, so that means that there's no circle on top. So in the very top, it's just going to be kind of like a, what do you call it then? It's not even going to be a circle. There's just no area then. Whereas for the great circle, right in the middle over there, if I create its annulus, that annulus is going to be the entire circle because h is equal to 0 in this case. Now, put it all together, if you can kind of see it then, okay, what I just drew right there is basically a cylinder. Okay, that right there is going to be a cylinder where if you notice the inside, the middle of the circle, that is going to get smaller and smaller and smaller. And it turns out, if I'm looking at it correctly, that the inside right here, this is what it looks like then. This right here is what it looks like. So if I drew it correctly, it actually looks like a cylindrical cone that is burrowed through into a cylinder. Okay, a cylindrical cone burrowed through into a cylinder then. So if I can find the volume of that thing, hey, we're pretty much all set. Because the top half of the circle, that's what's happening. And then the bottom half of the circle, well, it's exactly the same thing. We're going to have basically another cylindrical cone right in the middle then, as a result, that is getting burrowed through. Okay, so let's go ahead and put it all together. Let's see here. If I'm looking at it correctly, again, this is going to be equal to r, because that is the radius of the sphere. And then this guy right here, that's also equal to r because that's the radius of the sphere. So remember, what I'm trying to find is the following then. And let me just go ahead and draw it out one more time so you can kind of see it. I am trying to find the volume, right, of this cone, but I am going to minus, I'm trying to find the volume of this cylinder, but I'm trying to subtract the volume of the cone that's inside because the area, because the sphere is represented by the region that is kind of like in between the sand hourglass over here. So that means the area, the volume is going to be equal to pi r squared multiplied by 2r, because that's the area of the circle, which is pi r squared, multiplied by 2r because the height, well, that's 2r. But minus the two cones that you have in the middle, because that's the open space that makes the analyst then. So that is going to be 2 multiplied by the volume of the cone on the inside. That is equal to pi multiplied by r squared multiplied by 1/3. So those are going to be the two cones in there. So now I'm just going to clean up this formula right here. So pi on the outside looks like it's going to be 2 multiplied by r cubed, and then minus 2/3 multiplied by pi r, and then that is going to be cube also. Oh, wait, I forgot the r over here because remember, I forgot there's also the height of the cone that I need to multiply by. So this should be actually pi r cubed as well. So let's see, putting it all together, that is going to be pi r cubed multiplied by 2 minus 2/3. And if we clean that up, that's pi r cubed multiplied by 4 divided by 3. So that is going to be the volume of a sphere then. Okay. All right. Now that we have the volume of a sphere, which we can, easily use in this case, because we could just, if we know r, then we can just go ahead and find out the volume in this. Let's go ahead and look at the last part of it, which is the derivation of the surface area of the sphere. Okay. So I want to find out what is the surface area of the sphere. So for the surface area of the sphere, we're going to have to do something kind of strange then, okay? So let's go ahead and draw a sphere once again, okay? So here you have the great circle, and then here you have the sphere. And what I'm going to do is I'm going to go ahead and say that that is equal to r. What I'm going to do is I am going to, I guess, kind of like make another circle outside of it. Okay, so imagine if you have, like, say, a ball, and then around the ball you're going to put some putty on there, and then that will result in, say, a bigger circle that is going to be thicker than the original circle. So here, let's see if I can kind of draw that out then. So I'm going to go ahead and put kind of like a space in between, right? Imagine like putting like a layer of mud on top of the sphere. Okay, so there is going to be a small little surface area. There's going to be kind of like a layer of mud, which is what we're drawing out right there. But as a result, there is going to be a sphere that's going to be created over there as well also. That is going to, I guess, cover that entire ball then. So for that sphere, if it's uniformly, divided, I'm going to go ahead and say that that radius is going to be r plus h then. Okay, I'm going to say that the area, I'm going to say the radius is going to be r plus h. The surface area, okay, the surface area is going to be, now if it is, hopefully you can kind of see it. The surface area is going to be then that space kind of like in between. So let me see over here. Let me go ahead and use a black in this case. Okay, so the surface area is going to be pretty close to whatever the area of this thing is. Okay, whatever the area of this thing is, which is kind of like the area in between the two spheres. Now, it's going to be a little bit more than that because I need to make sure that if I'm trying to solve for the area, I need to make sure that h is going towards 0, because the closer h is to 0, the more accurate it is to become the surface area. So let's go ahead and write that out. The surface area is going to be equal to the outer sphere, so 4/3 pi times r plus h cubed, minus the surface area, the volume of the sphere of the inside. So 4/3 pi r plus h cubed. Okay. Now, I actually need to do a little bit more over here, okay? This right here, this whole thing is actually three-dimensional. The surface area is actually two-dimensional. So technically, this is not something that is, well, it isn't something that makes sense, because how can something two-dimensional equal to something that's three-dimensional? So here is kind of like the add-on then. So imagine that layer of, if you can imagine this layer of mud right here. What I'm going to do is I'm going to flatten the whole thing. Okay, I'm going to flatten this entire layer of mud. And as a result, then that's basically what it looks like. If I flatten it out, then that means that there is a small little thickness to it. Okay, that looks like the following. Okay. Because remember, there's a little thickness of layer of mud in this case right here. That little thickness right there, that is going to be my H right there. Okay, that is going to be my H. Whereas the surface area that I'm looking for, well, that's going to be the top part. So technically, for this equation to actually work, it should actually say the following then. The volume of the bigger sphere minus the volume of the smaller sphere is equal to the surface area multiplied by H, which is then the thickness of the, well, I guess the mud in this case, because now we have something that's three-dimensional equal to something that's three-dimensional. Okay. All right. So now that actually works out, let's go ahead and kind of clean up this area then. I will go ahead and multiply everything out on the right-hand side. So that is going to be 4/3 pi. And then for the inside over here, oh, actually, wait, the area, sorry, the volume of the sphere inside is not actually equal to 4/3 pi r plus h. It's just pi r squared, because that is supposed to be, yeah, the inside sphere then. Okay, so I do apologize for that. Okay, but anyhow, factor out the 4/3 pi that they all have in common. And then for the inside, we have r cubed. Actually, hold on. Sorry. It's r plus h cubed and then minus r cubed. Okay, and that's equal to the surface area, which is what I'm trying to solve for, multiplied by the height, or multiplied by h in this case, which is the thickness of that mud then. Cleaning up the algebra a little bit more, so that's 4/3 pi. And then for this part, if I expand it all out, that gives me r cubed plus 3r squared h, and then plus 3r times h squared plus h cubed, and then minus r to the third. So just saving you a little bit of time, if you multiply it out using FOIL, those are the four terms that you're supposed to get. And fortunately, in our case, the r cubes would actually cancel out. So that means that we have those three terms left. So once again, solving for the surface area, which is what I need, is equal to, and I might as well at this point divide by h from both sides. So the inside, we have 3r squared h, and then plus 3rh squared, and then plus h cubed, and then divide by h on the outside. And we can go ahead and divide through each term by h because they all contain h. So 4/3 pi multiplied by h multiplied in, or divided in. So that's 3r squared. And then we have plus 3rh and then plus h squared. And now here's the magical part. Remember what I said earlier. In order to get the surface area that I want, I would like h to be driven to be equal to be 0, because the closer the two spheres are to each other in terms of their radius, then that means that we actually get the surface area. So all my h term, if possible, we're going to go ahead and set equal to 0, because that will diminish h then. So as a result, all we have left is just the two front part over here. So the surface area is going to be 4/3 and then multiplied by pi, multiplied by 3, multiplied by r squared. So the 3's can cancel out. So it's 4 pi r squared. And that right there would be the surface area of a sphere then. Okay. All right. So there it is. That's the last derivation that we need. So we now have everything then. The volume of a sphere and also the surface area of a sphere. So let's take a look at this final problem right here. Find the volume and the surface area of the cone that is below. So, this is hopefully going to give us a closure to all of this. So let's start with the volume. I think that one is going to be the easy part. Okay, so the volume looks like it's going to consist of a semicircle, which is on top, and then a cone that's in the volume on the bottom. So if we can find out each one, then add them all up, then we're all done. So for the semicircle, that is going to be equal to 4/3 and then multiply by pi and then multiply by r cubed. And I am going to multiply by 1/2 because that is supposed to be a semicircle, not the entire circle. So that's the volume of the semicircle, that's the hemisphere that's on top. And then now I am going to add that with the volume of the cone that's on the bottom. Remember that 5 is also going to be the radius of the circle of that cone, of the base of the cone. So that means the volume is equal to 1/3 multiplied by pi, r, which is 5 squared multiplied by 12. So that, whatever it is, if you clean it up, that is going to be the volume then. So let's see here. Can we get a nice number out of this? So let's see, 4/3 pi multiplied by 125 multiplied by 1/2, and then plus 1/3 pi multiplied by 25 minus, multiplied by 12 then. Since I don't have, well, we can kind of clean this up. 4 pi over 3 multiplied by, actually 2 pi over 3 because the 4 and the 2 cancels out. So that is equal to 2 pi, 2 pi over 3, and then multiply by 125, and that is equal to a total of 250 pi divided by 3. So that is just the first part. Say 250 pi divided by 3. And then plus for the other part, looks like this guy right here, that's going to give us 300, and then divide by 3, that's going to be equal to 100 then. So plus 100 pi then. So that is going to be our total volume then for the whole thing. Now for the surface area, well, that calls for the surface area equation for each one of these. So for the sphere that's above it is going to be 4 pi multiplied by 5 squared, which is the normal surface area. And I'm going to multiply that by 1/2 because, well, it's only the hemisphere, not the whole sphere. Be very careful. The surface area does not include this circle that's in the middle because that's not being exposed. So we don't actually count that in there. But what I do need to also add is the surface area of the cone that's beneath. And if you recall, we do need to find out what is the length of the lateral edge. So here, let me go ahead and call that L right here, and I need to solve for L. If you wanted to, you can go ahead and take that 12 and bring it a little bit closer in, so you can see that there's a Pythagorean theorem. So L in this case, the lateral edge is equal to 13 then. So plus the surface area of a cone is supposed to be equal to pi multiplied by the lateral edge multiplied by the radius of the circle. So there we go. So now we just go ahead and clean everything up. So 125, it's 25 multiplied by 2, so that's 50 pi. And then plus, for the other part, that looks like it's going to be 65 pi, so it comes out a little bit cleaner. So 115 pi, that is going to be my surface area then, okay? And remember, for the sake of units, this one is unit squared, whereas this one is going to be unit cubed, okay? All right, well, thank you so much for watching, and I will see you in the near future then, hopefully. All right, have a good one. Bye-bye.